All right, we're going to get started. So what we're going to do, Mark and I are going to do here today is, Mark and I spent an afternoon a couple months ago or a month ago kind of whiteboarding out a problem that they had with surface discovery inside of PayPal, inside of Zoom. And we kind of came up with a pretty good solution to the problem. And what I'm going to do is I'm going to kind of talk through just the foundations of Kubernetes surface discovery and how it works. And then Mark is going to talk through how they went and built on top of those primitives and on top of those extension points to achieve and remain compatible with their internal service discovery system. So I think it was labeled as a panel, but it's not a panel. It's two talks. I'm laying foundation. Mark is building on the foundation. All right, so I'm Brandon Phillips. I'm the CTO and co-founder of CoreOS. CoreOS builds a bunch of open source projects and also enterprise products in this ecosystem. Tectonic is a pure upstream Kubernetes distribution of Kubernetes with a bunch of additional utilities packaged together that make it possible for enterprises to adopt Kubernetes. And Quay is our container build and hosting service. So what I'm going to be doing is walking through a few examples, going through very practical service discovery. It's going to take about 15 minutes or so. Very practical service discovery examples on top of Kubernetes. This is kind of a 101 level foundation setting. In all of these, I'm going to be using this tool called Minikube, which allows you to build or bring up simple single node etcd or simple single node Kubernetes clusters on your laptop. There's a quick start guide available here. If you search for github.com/kubernetes/minikube, it talks through just how to bring it up under Windows, Linux, and OS X. And then if you're interested in trying out the Rocket container engine, there's a couple of flags that change and you can bring up under Rocket. Once you get everything working, essentially it should look something like this: kubectl, git nodes, and you should have a single Minikube instance running. All right. So that's what I'll be using for all of the demonstrations. Wow. Don't want to go into auto advanced mode. I'm not going to cover it that quickly. So the first thing is we'll talk through Kubernetes label service discovery. So Kubernetes has this really powerful concept of labels that you can apply to essentially every single resource and object inside of Kubernetes. These resources or these labels are a concept inside of the Kubernetes API server. The API server you can think of as just any other web application. It's not really any magic or anything fancy. It's a container that stores all of its data in a persistent data store called etcd. It is hosted at a well-known URL. So generally, you'll have like kubernetes.internal.corp or whatever, and that'll be protected by TLS assets or TLS certs or by some sort of other identity like OpenID Connect or something else. So the API server is what your laptop talks to, and it's also what the applications running in the cluster talk to when they need to resolve a label or any other service discovery information inside of Kubernetes. So the idea of this label is that when I do something like kubectl and I create a new replica set or a new application that I want deployed inside of Kubernetes, various labels will be applied to it. And these are used throughout the system, not just for service discovery. So let's say that I deploy an application. This application is going to have a couple of labels like app equals web and environment equals prod. I'll deploy a replica set. Say I want to have 3 copies of that application running. Perhaps only one is running. So the replica set, the software that manages that replica set, is inside of a component in Kubernetes called the controller manager. That controller manager essentially is doing service discovery via the labels inside of the API, finding what is the current state based on that label query, saying, all right, well, based on the label query, the current state of the system is 1. I've been told that I need to move the system to 3, and then it goes through and launches new pods on top of the cluster. So this idea of labels and this idea of service discovery is fundamental throughout the entire Kubernetes system. So what we'll do is just give a practical example using the command line tool of how this works. So the first thing we're going to do is use kubectl run, launch an Nginx server, and then we're going to apply a label to that deployment, which will apply the label to the replica set, which will apply a label to the pod. So let's go ahead and look through there. So I'll do kubectl run, Nginx, et cetera. I've already done this because it takes a couple of seconds to download the container, and we're on conference Wi-Fi, and I don't want to bore you all. So the application is already running. Now what we can do is we can find, all right, well, where are all of the replica sets? Where are all the instances of this application? So if we do kubectl get replica set, which can be shortened as RS, and then do a query where we say, give me all the replica sets that match label, app equals Nginx, it returns 1. And similarly, we can do the same thing for the pod, which finds the actual concrete running process inside of the cluster. So again, that whole chain of commands is like, we're able to find the deployment. The deployment is the thing that kubectl run created for us to tell us to run this Nginx service. The deployment then creates replica sets. This is how rolling updates happen in deployments. So the replica set says, all right, I want to have 1 copy of this running. And then finally, we go down and we see that the pod has that same label, app equals Nginx, and we find the concrete running process, that concrete running container. Any questions on that so far? Good? So you can start to imagine this doing other things. You can, the concept of a service is that concrete load balancer inside of the system. So if I want to put this Nginx service behind a load balancer, I say, I want an IP address allocated. I want this IP address to be the central incoming load balancer that I'll maybe put into DNS or whatever. For my service, that load balancer will then use label queries to find all the pods that are running that can service that service. So it's very hierarchical. And then maybe you put that service behind an ELB or behind a load balancer inside of your data center, like an F5, or maybe you put that service directly on a network, like inside of a Google Cloud application. Okay, and the way that we do this with Minikube is because Minikube doesn't have a load balancer, we don't have an F5, we don't have anything fancy, is that we just directly expose the service via a thing called the node port. So that happened really fast, but what we're telling it is, all right, I have Nginx running. I want you to expose that Nginx deployment. I want you to expose port 80. I want to give it a node port. So what is a node port? If we go in and get the service, kubectl get service Nginx, so YAML. What we'll see here is that there's a thing called the node port that's been assigned along with the port that we want to target for this, the port that we want to target for this load balancer. And what this node port does is it says on every single node in our cluster, and if we remember, every single node in our cluster is this single node, this single Minikube node. On every single node in the cluster, we want to expose a port that is going to route to this application. And that port in particular is going to be 30,985. And it just randomly assigns it. So if you remember back before the world of Kubernetes, this is how we all did sort of internal service discovery, right? We had like single IP addresses for servers. Those single servers, when we needed to expose a port, we'd go into our Excel spreadsheet. We'd record, hey, I'm reserving port 4098 for the Redis cache or whatever it is. And then we'd tell network operations, all right, I need to use this port for that. And all the application developers would hard code that into their configuration. This is allowing us to go back to that port mapping world where we may not have sophisticated load balancers or networking. So after we get that placed, Minikube, the tool that we're using to run this, has this convenience application called Minikube Service. And what Minikube Service will do is it will figure out what operating system I'm on OS X or Windows or Linux. It'll run the correct command to launch my browser and actually open up that service on that port. So what happens is that you'll see this is the IP address of my Minikube, 172.16 something something, and then it opened up port 30,985, right? So immediately we're able to kind of simulate the idea of a load balancer here on our laptop. Any questions on that? Yes?
Does node port kind of load balance between your app? I think, or is it always like the pod, the container in the pod?
Yeah, great question. So the question was if node port always load balances to like the local machine or if it load balances across the cluster. And so what's actually happening behind the scenes is that there's a thing called the kube proxy, and every single machine in the cluster is going to expose that node port once you define a node port. So if you have 5 workers, all 5 workers will begin listening on 30,985. And then when they hit that machine, it will essentially do round robining through the IP tables system inside of the kernel to hit random hosts. And so generally what you'll want to do is you'll want to, like if you have an ELB or something, or you have an F5, you'll want to have that F5 load balance across your entire cluster, and then essentially you have a second like application tier that load balances through Kubernetes. This is all like just one way of doing load balancing. Obviously there are more Kubernetes native ways, but this is super convenient. Particularly we see a lot of people as they're getting early adopting Kubernetes inside of their environment or inside of their companies. They'll use node port as a way of not having to engage the network operations team right from the beginning. Great question. Any other questions? Okay. Okay, so this is all about the API, the Kubernetes API. We're using labels, we're using services, we're using deployments, and these are fundamental parts of the Kubernetes API. Now, above the API, there are a lot of conveniences that Kubernetes provides. The DNS add-on is one of those conveniences. So DNS is not built into Kubernetes. It is an extension point. It is something that is a convenience offered by Kubernetes, but it's something that's pluggable, and that's what Mark is going to be talking about, is plugging into DNS. So the DNS add-on, what it does is on every single machine in your system, you provide this IP address via the cluster DNS flag of the kubelet. And what happens is that every single pod launched on that machine, or on that machine with that flag, will get injected into its etc-resolve.conf, the IP address that's provided. And this IP address is a IP that exists on top of the Kubernetes network. So it's going to be a 10-dot network or whatever you defined as your Kubernetes service network. So it gets a little bit of meta and recursive here. So we're telling every single pod in the network, this is the IP address you should use, and that is part of the Kubernetes network. And so when a DNS query comes in, it gets routed over the Kubernetes network, hits another service, the kubedns service inside of Kubernetes, that's running DNS mask or whatever, and actually resolves that. So if we look into Kubernetes on this Minikube cluster, we'll run a query that says describe the service kubedns that's running inside of kube system namespace. And what we'll see is that there is a service that's running at 10.0.0.10, and it's exposing port 53, both UDP and TCP. And this, again, this IP address is injected into the etc-resolve.conf of every pod running in the cluster. So this is where they go to get their DNS resolution service. So the basics of this service, what happens is that there's this piece of software called the kubedns pod. It runs as a deployment in your Kubernetes cluster. It synchronizes with the API server. So it's asking the API server, give me all the services that have been defined, give me all the pods that have been defined, and it's creating essentially a cache of all those things that it can resolve as DNS requests. And then it's exposing the service 10.0.0.10. So if you were to go on to one of the pods in the system and run dig, you'd say dig at this IP address, and you could say resolve the DNS service itself, which runs at kube-dns.kubesystem.service.cluster.local. Straightforward. Now, it's kind of annoying to constantly have to be SSHing into the cluster if you want to understand the system. So I'll post these slides later, but if you just Google like Kubernetes network troubleshooting CoreOS, we have this one-liner here that will port forward the Kubernetes DNS server to your local machine. So I'll go ahead and run that. And so what this will do is Kubernetes is going to run its DNS server, port forward its DNS server to port 5300 on my laptop. All right. By doing that, what I can do is I can start to play around with the Kubernetes DNS server. So I can run dig, and I can see, I can run dig, and I can see, ask a question like the cluster.local subdomain, which is the top-level domain of the cluster. And it gives me back the SOA record with the name server. The next thing I could do is I can start to resolve services. So I have a service inside of my cluster. If we do kubectl get service, I have a service inside of my cluster called etcd-cluster.001. And if I do a dig for that service for an A record, I'll get back the cluster IP. So if I do etcd cluster.001.default.service.cluster.local, I'll see here that I get the exact same service IP back that is listed here inside of the service list. And similarly, you can do serve records as well. It will, if you have a service that, like the DNS service that expose a TCP and UDP port, you can dig for service records and find out what port number it is based on the protocol. There's a bunch of other features that the DNS add-on has. One of the most convenient is that it will automatically put a search prefix for the DNS. So for an individual pod, let's assume that you want to hard code inside of your application. I want to be able to reach Postgres. You can just say Postgres. You can expose a service called Postgres in your namespace, and that will just automatically resolve. And you won't have to do any of the prefixing, like adding cluster.local or anything that I'm having to do here, because the etcresolve.conf search prefix will already be in there. There's some really good docs, or at least some passable docs that I helped to write about Kubernetes and the DNS add-on and a lot of the default functionality. It's kubernetes.io/docs/admin/DNS. And it describes all the different types of records and all the different types of queries that you can make against the DNS server. That is the end of part one. So what I'll ask next is I'll ask Mark to come up and start setting up. And meanwhile, I'll take a few questions if anybody has some on how this all works. Yes?
I think you were hinting at where we go to find this out. Can you touch on what you get back for SRV queries?
Sure. So the question was, what do you get back for SRV queries? So on a service, what you'll get back on an SRV query is you can do things like underscore DNS underscore TCP dot service will give you back the port and then the rest of the SRV record. There are, I'll have to look again. I believe that it will, I'll have to look. I think on some of them, if you have multiple IPs, it'll return all the IPs as well for the service. But I'll have to check on that. It's true.
Yeah, we did it for create cluster.
Okay.
So once a node joins, you, for example, have to create cluster, do DNS service record lookup. So once a new node starts, does the service record lookup, and then you get all the other nodes that are in the cluster.
Yep.
That's cool for that.
Yeah. Yep. Yep. Does that answer your question? Yeah, please. Yeah, so the question was how quickly do new services get registered? Generally, it's sub-second registration. The KubeDNS add-on is doing a thing called watch on the API, so it'll get a streaming update essentially as soon as new stuff shows up. Yeah.
So what it might use service appears to modify its host on the
Yeah, so it doesn't modify etc hosts. So this is an actual real DNS server, a caching forwarding DNS server. And so this essentially will do the recursive resolution, and it runs DNS mask in front of it. etc hosts is completely untouched. It essentially only does the etc resolve conf search and resolution. All right, with that, I will hand it over to Mark. Thanks so much. Oh, you'll need a mic.
Okay. Thank you, Brandon. My name is Mark Petrovic. I'm an engineer at PayPal. More specifically, I'm an engineer at a company called Zoom, which is a PayPal company. We were acquired late last year, and Zoom is a money service whereby we help folks living in the United States send money back home every payday to their families back home in any number of any one country among dozens of countries that we service. So we are about 100 some odd engineers, and we're in the process of containerizing all of our microservices, as well as vacating our legacy monolith. So I'll tell you how we're doing that in a second. Briefly on the matter of what challenges we've faced along the way, some specific to integrating our legacy service discovery, some not. But if you've started down the path of containerizing your applications, you probably have noticed that it touches everything. Your builds are affected, your CI pipeline is affected, how you deploy is affected, how you talk about deploying is affected. If you haven't started containerizing your applications, then you can expect to rediscover how containerizing will touch everything. So under that umbrella of a lot of my tooling is going to change and my language is going to change, language about how I talk about deployments will change, there are a couple of interesting things that we discovered along the way, unrelated to service discovery, but I'll mention them anyway because I think it's worth it. For example, if you have logging dashboards or metrics collection dashboards, and the folks who read those dashboards, if they're accustomed, based upon how you deploy, they're accustomed to seeing a particular application always logging from a particular host or a particular IP address, then you should visit with them now, because container IPs and container host names are not persistent things. Every time you restart a container, it gets a new IP address. It gets a new host name. So if your logging framework or your metrics collection framework has customers, internal customers who are used to seeing artifacts of your deployment whereby applications always log from the same host, go visit with those folks and tell them that with containers, an application will retain its identity, but it will be logging from a different host every single time, and a different IP address every time that application is deployed. We're also facing the challenge of crafting developer environments for our developers, 100 some odd developers. Currently, developers at Zoom will deploy their dependencies onto their laptops and then begin to develop against those locally running dependencies. What we want to do is to give developers their own Kubernetes cluster, a small cluster, so that they can begin to deploy in the same way that their counterparts in QA and production will deploy applications, so that we can all talk about deployment in the same way, not in terms of Puppet configurations, Puppet modules, Ansible scripts, but instead speak in terms of Kubernetes first principles like replication controllers, deployments, namespaces, secrets, things like that. So we want to give developers their own clusters, and we're working on a couple of ways to do that. If you are currently doing that, or you have solved this problem, I would like to talk to you in the hallway. Maybe we can share notes. So developers are going to have to become familiar with how kubecontrol works, which is the command line tool with which you control a cluster, as well as the staff in QA and production will also become familiar with kubecontrol. So Kubernetes and its control mechanisms will be part of the vocabulary of how we talk about deployment, which is an educational problem across the organization. You'll have to teach yourselves how to do this. Finally, the challenge we face is integrating our legacy service discovery design into Kubernetes so that some applications can run inside the cluster on day one, and some will continue to run outside the cluster. We're going to production with Kubernetes sometime next year. We're preparing with our plan to do so. So we want to start slowly, deploy 1 or 2 applications into Kubernetes, and have everything else continue to run outside. But these applications can't know that they're running inside the cluster, nor can applications that need them know that they're running in the cluster. That would be counterproductive. So I'll share with you how a couple of designs that we came up with that lets us move applications into the cluster seamlessly. So we've been in business for 10 some odd years, and we have legacy that we're dealing with. We have traditionally run a monolith that manifested all of our business logic. New functionality we're implementing in microservices immediately, and we're setting aside time to vacate our monolith of its functionality so that someday we'll have just a set of cooperating microservices. We are containerizing everything. We have started down this path a good year ago, and if you are just starting this or you contemplate starting it, you will discover that it takes you and your organization many, many months to surface how you work. What is your Docker file? What should your Docker file contain, or your AC build file? What does my container entry point look like for all of these microservices? And hopefully you'll come up with a model where all of my microservices have pretty much the same Docker file, hopefully the same Docker file. Not the same instance, but they read the same. And hopefully you'll find that your applications all can use the exact same entry point, which in our case is a shell script. We found that shell scripts are universally sort of the entry point that just falls out of most designs. So your entry point will read a certain way, your Docker file will read a certain way, and if you're an organization of any size, it will take you many months to surface what those patterns are so that you can move on to the next problem. So we also need an orchestration framework. We've decided to use Kubernetes many months ago. And I'll tell you how we've integrated our service discovery into this thing. So we currently run our microservices on bare metal or VMs. And we don't know what IP address a microservice will take on when it begins to run. By design, we don't know, or future clients of that microservice don't know the IP address of that microservice running right now in production. Intentionally, we want to develop a way where clients that need that microservice can discover its address just in time. So we need a service discovery framework. A couple of years ago, we were inspired by Airbnb's Smart Stack technology to write our own sidecar application that we call Service Proxy. So Service Proxy is designed to run on every host on which applications run. So in the future, we're going to be forklifting our own Service Proxy out of the design, and we're going to swap in Linkerd, which does better load balancing and it does request tracing. Changing out Service Proxy for Linkerd should be transparent and just a drop-in replacement for us. But nonetheless, Service Proxy rests on a DNS trick, whereby when our applications come up and register, they assert their name and the IP address at which they currently run. They post that to Service Proxy, and Service Proxy remembers that binding so that when clients come calling for that name, Service Proxy knows where to find it. So the big blue box is a physical host. This is how we currently run. Big blue box is a physical host. On every host is a Service Proxy instance, which is an HTTP proxy. So on this particular host, there's an application foo and bar running. So when bar comes up, it posts a request to service.1.zoom API. We've hijacked the top-level domain Zoom API to return 127.0.0.1 in response to any question asked on it. So service.1, 1 is the version number. Service.1.zoom API resolves to 127.0.0.1, which finds bar posting to the local host Service Proxy with an assertion that my name is bar and my IP address is such and such. Please record me in the system of record as being there when someone comes calling for me. So someone is foo. Foo comes up and it needs to consume bar. It forms the URL with bar.1.zoom API as the host name part. That name also resolves to 127.0.0.1. Service Proxy running on the node gets a hold of the request, looks at the host header and says, this is for bar. I know where bar is. Bar registered a moment ago. I will proxy that request end-to-end on behalf of the caller, foo. Foo doesn't know the Service Proxy is there. All it knows is that it got an answer from something going by the name bar.1.zoom API. Bar doesn't know Service Proxy is there either. Through tricks of DNS, Service Proxy is insinuated into the call path for both of these clients. For bar during registration, for foo to consume bar. So if you want to port this pattern into Kubernetes, the first thing that comes to mind is I'm going to bundle a Service Proxy into every application pod, because the way that the Kubernetes pod networking works is such that containers within a pod can address each other on localhost by port alone. So without changing how my DNS returns 127.0.0.1 to every question, I can move a Service Proxy into the pod, and when foo or bar wants to interact with any name on Zoom API, it's returned again the answer 127.0.0.1, and lo and behold, there's a Service Proxy in that pod with that application that can be addressed at localhost and the well-known port of Service Proxy. So this does work. This works very well. It works exactly as it was intended to work with respect to the localhost trick inside of a Kubernetes pod. We could stop here if we had gobs of memory. We could stop here. But we always want more. We don't have gobs of memory. We want to see if we can advance this model to improve it. The reason that you don't want this model long term is because if you have many pods or many applications, every application will have many replicas. You end up having that number of Service Proxy instances on your network. And for us, Service Proxy is a Java application. So a Java application that has been warmed up doing production work will typically want hundreds of megabytes of memory to run. So you don't want to have to consume hundreds of megabytes per pod on your network. So there are a number of ways forward from here to improve this model. This is the model that we've come up with, and it reads like this. It depends on three things. The first trick is to pull Service Proxy out of the pod and run it as a daemon set on each node. Daemon set with a capital D is a Kubernetes thing whereby you can get a pod to run on a per node basis. Useful for things that need to run as classic daemons on a host. I need one of these things running on every host. It's the standard Unix daemon model. So you pull service proxy out of the pod, put it on the node, run it in the host namespace. The second piece of the solution is to run DNS mask as a daemon set, also in the host network. DNS mask, if you don't know, is a lightweight name server. We program DNS mask in its entry point, which I'll show you in a second, to return the node IP as the answer to any question on the domain Zoom API. So I've hijacked the top-level domain again in a slightly different way using DNS mask as a mildly programmable web server, or DNS server. The third leg is to configure your kubelet on every node to deposit the node's own IP address as a name server inside of each container's resolve.conf file. So now when the container goes to look up any name, it's directed to the node IP, which turns out to be DNS mask running on that node in the host's network namespace, returning the node IP itself in response to any question on Zoom API, which, when you want to interact with a host in that domain, sends the request to service proxy running on the node in the host's network namespace. So this is the functional equivalent of locating a service proxy inside of every pod. And this works. And the advantage of this model over the previous model is that now I have one service proxy instance running on my node rather than one in each pod. The downside is that I have to run DNS mask as a daemon set, which is not a big deal. DNS mask is not resource hungry. Yes?
How is the DNS mask different from what you're asking?
Say that again, I'm sorry.
How is what you're asking, I didn't follow, how is the DNS mask change different from what you're asking from the proxy that you said?
DNS mask is a way that I can figure out where the service proxy is running to direct clients to interact with service proxy on the node instead of service proxy on localhost, which is what the previous DNS answers were returning in the old world order. Not better?
So if you make a request inside one of those pods, what's going to happen?
If I make a request for any name inside of one of those pods, the name server for that pod is DNS mask running on the node. I'll show you the entry point for DNS mask shortly to show you how it discriminates between questions on Zoom API and all other questions. But it gets a hold of the name server query request so that it can do the right thing with the request based upon the domain of the request. Here is the entry point, the shell script entry point for DNS mask itself. The 3 dots I have deleted, but consist basically of parsing In order to get the node IP address here for DNS mask, if you're familiar with DNS mask and how it's configured, this -- address flag says, for any requests on the domain Zoom API, return the node IP. I acquire the node IP just above this line by parsing the output of ifconfig on eth0. That's how I come up with my node IP. And because DNS mask is running in the host namespace, this is the same IP that service proxy is running on because it too is running in the host's namespace. So there's a GitHub repository that's associated with these slides you can find in the conference proceedings that show how I acquire the node IP, but it's basically parse the output of ifconfig. I also want to mention briefly that our pod IPs are fully routable. There are a lot of different ways that you can arrange for pods to be networked amongst each other. But we're using the Calico network tooling to make our pod IPs fully routable on the network so that when I address any one of my microservices by IP address, that routing doesn't have to traverse encapsulation or NAT or special ingress controllers to make its way to the destination. It's fully routed, pod IPs are fully routed on the network. So that's not central to how we're doing service discovery, but it certainly helps us to land some microservices inside the cluster, keep some outside the cluster on day one, and have all of these entities being routable for each other without doing special encapsulation or NAT or ingress controllers. So that's how we have ported our legacy service discovery into Kubernetes with none of the technology that Brandon was originally describing. That's for a different use case. We'll probably use some of that stuff, but not for this purpose. So thank you very kindly. I think we have time for a couple of questions. Yes? Sir? The reason we don't use any of the Kubernetes native service discovery is because we didn't want to introduce that much change to our existing design, the way our services currently find each other. We're suffering enough change as it is, porting our applications into Kubernetes and changing our organization's tooling. So we have settled on, let's port the existing service discovery mechanism into Kubernetes and don't touch the other Kubernetes magic service discovery at all. Yes? Nothing. The third piece was the kubelet, which has been told to deposit the node's IP address into the resolve.conf of every container. That's the last piece of glue to direct containers to use DNS mask on the node for their name server. So thank you very kindly. I love Kubernetes. The community is super welcoming, eminently competent, and I learn something every day I deal with these folks. Thank you so much.